Okay, last time we had talked about, we just finished up on braze joints and pointed out there's contact strengthening. So the thinner the braze joint, the stronger, although you really got to get down to about 1/1000th of an inch thick to start seeing much of an effect. And then we talked about this plot of fusion welding processes, pointed out that all fusion welding processes have to lie on here. It's fundamental. It has to do with surface heating. If I heat a material from the surface to try to melt it, and you look at the rate at which the heat diffuses in and the time it takes for the surface to reach the melting temperature, you've got to lie between 10 to the third and 10 to the 6th watts per square centimeter. To give you an idea, the surface, the heat intensity or power intensity from the sun is not 100, but it's like watts per square centimeter, but it's like 0.05 watts per square centimeter. So a simple flame, an air burning flame, air fuel gas flame, such as one of these, is about 500 times as intense as the surface of as the sun hitting your body. And you know that. I mean, it takes you 500 times as long to get a sunburn as it does to do it here, right? You can run your finger through there, but you do it quickly in terms of trying to prevent a burn. However, there's one place in the world that, and you ought to all go visit it, where they actually have, the mountains are such that they actually get 1.3 suns of, on a bright sunny day, you can get a sunburn there quicker than anywhere. It's on Maui, okay? So if you want to go to Hawaii, the way the mountains reflect the light, they actually get the intensity of 1.3 suns. So 30% greater heat intensity. There's a number of interesting things about Maui as far as that goes. Actually, Maui has it has the largest mountain by volume, not the tallest, but Mount Haleakala just spreads way out at its base. It's got a huge base. And so if you take the volume of dirt, okay, that makes it up, it's the largest mountain in the world. But even more interesting to me on Haleakala is if you can get any climate in the world on Maui, from the tropics down at the base, and on one side it's wet tropics, on the other side it's the desert tropics. So you can get, and then at the top it's snow. You know, it's the top of the mountain. So you can get any degree of wet by going around, and you can get any degree of cold or heat almost by going up and down. So it turns out the United Nations used to have a research laboratory there to grow beans because they could reproduce the climates of any place in the world depending on where around the mountain they were growing their beans. But anyway, so we kind of put this up, and I wrote down that based on this and based on heat flow, the heat affected zone size is controlled by heat flow, the travel speed is determined by heat flow, the heating efficiency, the need to automate because your interaction time is related to your travel speed or inverse of your travel speed. And if you go too fast, you don't have something that people can respond to. If you have to automate this thing in great detail, or you go to higher power density heat source, it increases the cost of the equipment, and it has increased production volume requirements. What we didn't talk about was the depth to width ratio of the weld pool, and turns out that if I'm over here at 10 to the third, I will have a weld pool, if I did an oxyacetylene weld, that might have a depth to width ratio, that's what we usually talk about, of 0.1 to 0.2, 5 or 10 to 1 width to depth. Here you'll have something on the order, theoretically 0.5, but it's going to 0.3 to, well, let me just, 0.3 to 1.0. It turns out you can actually get something deeper than a hemisphere for other reasons we'll talk about later. And over here, it turns out you can get a depth to width ratio. So this one, if you want to look at it, might be something like that. The depth to width ratio for a laser electron beam, where we're essentially doing hole drilling, people have actually done 200 to 1. Okay, a depth to width. In practice, 10 to 1 is about the greatest you want. And so in practice, you want something that looks like that or so. Does anybody know why you don't want something that's 200 to 1? The British Welding Institute has actually welded like a 20-inch thick chunk of aluminum in a single pass with an electron beam. The problem is if you're off axis the least little bit, then you miss the joint. You know, I mean, if you're talking about, if you had 200, well, first of all, they did it at 200 centimeters or whatever, okay? And they had something that was a centimeter wide. But even so, if you have a little bit of angular misalignment, you're going to miss your joint. If you have a little bit of transverse misalignment, you're going to miss your joint. So the other problem is these sides, we're going to talk about it when we get there, these sides have to be perfectly straight. If there's some curvature to them, if you had a weld pool that looked like this and had some inflection points in here, you'll end up solidifying this stuff just by straight heat flow and leaving a void as the metal cools right there in the center. Okay, and that's the problem. So it turns out you have to have excellent beam optics, you have to have fantastic alignment in order to do something at 200 to 1 or even 50 to 1. So in practice, about the highest anybody goes is about 10 to 1. So that's something that allows you, or this thing up here is something that allows you to figure out if someone comes up with a new welding process, a new heat source for fusion welding, it allows you to figure out all kinds of things and estimate all these different parameters here to figure out what's going to happen. And in fact, that happened to me about, well, it's happened to me a number of times, but to give you an example, back about 10 or 12 years ago, peace was breaking out, and the Defense Department had spent $250 million trying to develop particle beam weapons. This was actually an application to shoot electron beams through the air, and they wanted to do it, be able to shoot these things through the air for about 30 miles. And the idea was this directed energy weapon. If you had some incoming missile, this was not, when they started this program in the 80s, it wasn't all that many years since the Falkland Islands War, and the Exocet missile came in, and everybody was kind of sensitized to a relatively small missile coming in right over the water could wipe out a cruiser if its superstructure was made out of aluminum. It had to help out by providing fuel for you, but for your fire. But nonetheless, people were worried about that, and so they spent all this money trying to develop these high-power electron beams. And they were high power. They also had very high voltage. They built one of them at 45 megavolts. And one of the problems at 45 megavolts is once you get above 10 million volts, you get above what they call the activation limit. And that's where the electrons have enough power, they start to turn the nucleus into radioactive material. So you can start out with a non-radioactive material and turn it into a radioactive material. And that creates problems for the people doing research. So they had to bury this thing in the ground, and you get lots of radiation off these things at those types of voltages. But anyway, they'd spent $250 million, and it turns out they never did get 30 miles. They actually got 30 inches shooting it. But the problem was they ran into something called a hose instability. And a hose instability is named after the garden hose. If you take a garden hose and you just squirt water through it, it will start whipping around, like that. And the electron beam would do that same thing in the air. So it turns out you might be able to shoot an electron beam theoretically in the air for 30 miles, but you'd have to have a very cooperative target that runs into your beam. Okay, you can't aim your beam. So anyway, they were looking for something to do with these things, and since although the Defense Department and DARPA had funded it, they were working with the Navy, and so the Navy said, well, couldn't we do something with it like weld ships? And I said, they had a workshop for a couple of days, and they asked me to come down. And I said, as they explained all these things to me, I said, well, you might be able to melt chips, but you wouldn't, it turns out you only need, for welding in general, something on the order of 10 to 50 kilowatts of power. You don't need megawatts of power. I mean, you're only trying to melt a fairly small region. You're not trying to melt some great big casting. But in fact, there was a program for about 8 or 10 years to try to figure out what to do with these things. That, to me, is just an example of whenever someone comes up with a new heat source, one of the first things they will try to do is figure out how to use it for welding. Sir Humphrey Davy, when he first invented or discovered the electric arc, he was the one who called it an arc. And it's called an arc because he had two electrodes like this, and the arc formed an arch. Okay, the heating gases basically were rising, in the gravitational field, and formed an arch between the two electrodes, so he called it an arc. And that was in 1806, and one of the first things he did with it was try to weld with it. Well, no one ended up welding with electric arcs commercially until the 1880s, really, when Edison and Westinghouse came along and provided a cheap source of electricity. They didn't have a uniform source of electricity before that. So anyway, we've got this power density curve, and you can figure out where different welding processes lie, and we're going to talk about some of those processes so far as that goes. This thing only applies to surface heating. There are a couple of cases that I know of, two that I can think of, where you actually heat a metal internally. Anybody think of how you do volumetric heating rather than surface heating? Actually, there's three I can think of. Run a current through it, okay? Just a DC current, and in fact, people will weld rods together in a steel mill or somewhere. You just butt them together, and at the interface you have electrical resistance, a higher resistance than in the bulk of the material, and you pass a few thousand amps, or maybe 5,000 or 10,000, depending on the diameter of the rod, for a few seconds, and the thing will heat up there, and you just kind of forge the stuff together, and it's basically a diffusion, or it's a forge weld. It's a solid state weld. You haven't melted metal necessarily. A resistance spot weld, invented by Elihu Thomson here at MIT back in the 1880s and 1890s, you just have two big copper electrodes between two sheets, and the copper electrodes squeeze everything together, and you pass a current of 10,000 amps for a fraction of a second, and you weld them together. That's DC. There's an AC technique, whereas basically you go to a high enough frequency, and you can do induction heating. Induction heating is you have a high frequency coil around your metal part, and you induce a magnetic field, an alternating magnetic field. The magnetic field creates eddy currents within the part. So the alternating AC field induces current flow within the part. So it's still electric current, just like you said, only it's AC driven. There's actually no contact with the part, and so you can heat a part by induction. And so people do induction heating and forge welding and things like that. And actually the third one is essentially these high voltage, these megavolt electron beams. It turns out if I'm trying, well, actually I'll put this thing back up. Remember we said that at 10 to the 6 watts per square centimeter, you have such a high heat intensity, you just vaporize the surface. And if you go above 10 to the 6, you actually vaporize it so quickly the stuff just starts spewing off as a vapor, and you drill a hole through the part. It turns out if you, instead of using a 100,000 volt electron beam, you use a 2 or 3 million volt electron beam, you can overcome that surface heating because the electrons are actually deposited, have enough energy that deposited a millimeter or two deep beneath the surface. And so you don't get just this straight surface heating. You actually are heating a volume of several millimeters depending on how many million electron volts you get. Now at the same time you're getting tremendous amounts of x-rays, and you have to use like 1 meter thick or 2 meter thick concrete walls to shield yourself from the x-rays. So it's not exactly the most practical thing, but you can get volumetric heating by just very high voltage electrons. And in fact that means that you can actually get you can input power much more quickly because you're not limited by the overheating of the surface. So you can actually get 5 or 10 times as much power in to the metal when you do some slightly surface volumetric heating. Okay, so now I want to go back and start looking over here at 10 to the third, which is flames, and there's lots of interesting things about flames. If you were ever a chemical engineer or an aeronautical engineer and study combustion, let's see how this shows up. Not very well. Okay, let's try to zoom that down. There are, that's a little better, 3 basic types of flames. One is a diffuse flame, and you put the fuel and the oxidant into your system, and they actually mix out in the open at 1 atmosphere pressure. You can either do it as fuel and oxygen coming in, and they both come out at the same time, but they haven't pre-mixed, or you can just put the fuel in and squirt the fuel out, and it burns in oxygen from coming in, diffusing in from the air. Now, that's a diffuse flame. Essentially, the type of diffuse flame you're familiar with is a bonfire or a fire in a fireplace. The fuel is the vaporizing wood or whatever you've got is the fuel. A candle is a diffuse flame. You basically have a little wick that burns and kind of holds the flame in one spot, and what's happening is the molten wax is wicking up the wick. It flows by capillary action to this carbonized wick, which is porous. It vaporizes off, so the fuel is being vaporized out of this wick, and then the air comes in, and you get, actually the candle will look fairly steady, but if you have a little bit of a wind, it'll blow to the side. So it's called a diffuse flame because you're diffusing the oxidant into the fuel, and you're burning well away from the stoichiometric ideal composition of fuel to oxygen. The next one is a premix flame, and that's what we usually use most of the time in welding or brazing and soldering. And this is a premix flame. And I mean, it makes a little more noise because it moves a little faster because it's at a higher temperature than a diffuse flame. And where's the premixing? Where's the oxygen on this? You ever looked at one of these things? It's got holes down here. Okay? And so you're aspirating in. If you look carefully at this thing, you would find a little hole, a little orifice. And so that's giving you a high velocity coming out, and the high velocity by Bernoulli of the gas coming through creates a little suction, a little vacuum, and that aspirates air in here. The mixing chamber is right in here. If I were to take the tip off, there is, just basically doesn't work quite as well without the tip to concentrate it. The tip has a little turbulator in it, a little fan-shaped thing to help with the mixing process. But here's the gas just blowing through. This thing's got it's designed with a little piezoelectric start. That's what the trigger does. If I put the tip back on, and I have the turbulator to help improve the mixing, I can get a steady flame like that. Okay. So I have a pre-mixing in the chamber, but not ignition in the chamber, and the thing shoots out at a much higher velocity, somewhere typically 1 to 100 times the velocity of a diffuse flame, depending on how I've done it. So this is burning at 1 atmosphere pressure. This is also burning at 1 atmosphere pressure, but this is something much closer to the stoichiometric ratio. I don't have excess fuel in this. If I had excess fuel, what color would the flame be? Orange or yellow. Basically, it will glow because the soot particles from the unburned fuel, I mean, even though this is propane, I'm going to form carbon. If I got excess fuel, I'm going to strip off the hydrogen, and I'm going to end up with carbon, and those little carbon soot particles are going to get hot enough to start glowing back at me, and it's the glow. That's where I see the yellow or the orange flame. And if you've ever turned on a torch, an oxyacetylene torch, and before you turn the oxygen on, this thing shoots out a yellow flame and black soot all over the place, okay, because it's fuel rich. And actually, I think I gave you the copy of the paper I wrote on the World Trade Center collapse, where people, there's lots of theories on that. The World Trade Center was a diffuse flame, okay? There was no pre-mixing chamber. And in the diffuse flame, it also was fuel-rich. We know it's fuel-rich. You saw the black smoke, okay? And the reason it was so fuel, there's a huge amount of fuel there, and the air had to diffuse in. The rate of burning on something like that is limited by the rate at which the oxygen is brought in from the outside, and you have all this excess soot. So what we usually use is some sort of torch like this, and it turns out that if I change my oxidant from air to pure oxygen, I'll get that 100-time velocity because I'm not carrying around all this excess nitrogen. And the third type of flame is called a jet burner, and the jet burner is not used very often industrially except in jet engines. In that case, you essentially mix and ignite your fuels in a constant volume chamber. So you get constant volume burning rather than constant pressure, and you'll get another factor of 5 or 10 times increase in the velocity of the premixed flame. Okay, so it turns out the velocity of the flame is critical towards the amount of heat intensity I can get on that surface, and we'll talk about that in a second. But this jet burner, you're not necessarily getting any more temperature, but you're doing it at constant velocity, so all that PDV work is shooting out the orifice rather than kind of being wasted in a premixed flame, just expanding against the atmosphere at constant pressure. There are commercial applications, a few, for jet burners. One is to drill holes in rock. It turns out with the jet burner, you can get about 1,000 or 2,000 watts per square centimeter. And it turns out that if you're down in a hole in some rock and you have this jet burner and you can get 1,000 to 2,000 watts per square centimeter down in the bottom of that hole, because of the low thermal conductivity of the rock, this stuff is going to expand. It's a brittle material. As it expands in this confined hole, it's going to form little cracks, and it will essentially ablate away. And this thing has got a high enough velocity coming in here at 500 miles an hour, or over 100 miles an hour, let's say, that it just takes those little pieces of rock and blows them right back up the hole, because all that gas going down the hole has to come back out the hole. And it turns out you can drill much faster than mechanical drilling with tool bits and things like that, as long as you got the right type of rock and you don't have too much moisture in the rock and things like that. But it can be a very, very efficient process. They used to use it in the early 50s and 60s. The problem is you can generate something like 140 decibels. Remember, 80 decibels or 85 decibels is a lawnmower, okay, going. It's pretty noisy. 140 decibels, you can blow out your eardrums in minutes or hours. So they quit doing it in the 70s. I understand in the 90s they've actually brought it back, and they've got better ear protection for people and stuff. They brought it back because it's such an efficient process. So they do use jet burners for not just jet engines, but for drilling through rock and stuff. Force? The force is actually not as high as you might think. And mostly it's because you got a rarefied gas. You got a hot gas, and it doesn't have much density. And so typically, you're talking a few pounds or a few tens of pounds. You're not talking hundreds of pounds of force. And of course, it depends on the area that you've got and things like that. But the pressure, I guess it's easier for me to think in terms of pressure. It's probably half a PSI to a few PSI. And so if you got that over a couple of inches, you're going to get, what, 10 pounds or something. So you're not gonna knock someone over that way. You might burn them pretty badly, but you're not gonna knock them over. Okay, it's no worse than a bad hurricane. Okay, if it hit you in the face, and it's a very localized hurricane. It is kind of bad in terms of the temperature. It's a lot hotter than a hurricane, but let's face it. I mean, actually, when they first had the first railway in like 1815 in England or something, and the railway is horse-drawn or something. I think it's horse-drawn, or maybe it was the steam engine, and they were going to put it on a railway. And they had horse-drawn railways before. But there were people who said that people would suffocate because if you went 15 miles an hour, the wind would go so fast you wouldn't be able to breathe. Well, given the fact that someone running fast is 25 miles an hour, the people who said that, weren't really thinking. It just shows that people were stupid even back then and didn't understand science, really. So the surface heating by flames, the combustion intensity, CI is what people typically call it, actually has units of watts per square centimeter, and it's related to the heating value of the gas, how many joules per cubic meter in this gas that you're generating from the flame, how much enthalpy is released by the combustion, and the rate at which you're bringing it to the surface, which is meters per second. And it turns out if you do that, you're going to end up with units of joules per square meter per second, which is watts per square centimeter, or watts per square meter. Anyway, it has the same units, watts per length squared. And it turns out the heating value of the gas, the enthalpy, is directly related to the temperature. And the gas velocity is also directly related to the temperature, because the gas velocity in a flame is just related to the thermal expansion of the gas. The higher the temperature, the more thermal expansion, and therefore the higher velocity. So it turns out the combustion intensity goes as the temperature squared to a very rough first approximation. It turns out the theoretical heat flux is, if you do this combustion intensity, is about 10 to 50 times greater than what you actually measure in an air or oxygen fuel flame. An air flame is over here at about 10 squared. So if I've got propane C3H8 burning in air, I might have 100 watts per square centimeter. If I've got, if I've got acetylene C2H2 burning in oxygen, I can get 1,000 watts per square centimeter. Because I don't carry that nitrogen around, I get a higher temperature because I don't have all that nitrogen that I have to heat up. And we'll talk about these temperatures in a second. But in addition, because I get the higher temperature, I get a higher burning velocity, and that gives me a much higher combustion intensity. However, that's the rate I'm generating heat. But if I actually measure the heat flux to the surface, I only get 2 to 10% of that heat actually into the bulk of the material. And does anybody know the reason why we are so inefficient? Gas boundary layers. Does everyone know what a gas boundary layer is? Right? Fortunately, it's the same as a liquid boundary layer, right? A fluid boundary layer. Pardon me? Well, it's really unfortunate because you have to solve it, right? You solve the differential equations. That's what makes it. Otherwise, as a concept, it's not necessarily so bad. It is harmful in a lot of ways for other things, but it's actually beneficial in some cases. But you know what assuming we all know what a boundary layer is, we basically have the gas coming out of some orifice. As it hits the surface, there's stagnation or the no-slip condition along the interface. And that means that as the material comes across here, the velocity gradient goes from 0 up to the free stream velocity, and that's what this thing's trying to show over here. And you end up with a gas boundary layer. So the heat actually has to diffuse across this stagnant gas layer. It's an insulating gas layer. And as long as that's there, you're going to get very low heat intensity. If I go much faster in my velocity, I'll get a thinner boundary layer and I'll get better heat transfer. And that's why higher temperature flames give a big increase in combustion intensity in terms of what actually hits the surface. So if we look at temperatures of flames, let's put that down a little bit. Temperatures of flames, the first thing is the enthalpy of the reaction. The second thing is the stoichiometry of the oxygen-fuel ratio. And the last thing is, do you still have nitrogen around in the air, or are you burning with pure oxygen? The combustion velocity, that's temperature of the flames. Combustion velocity goes as a square of that temperature approximately. Pure oxygen gives about 10 times the velocity of an air flame because it has about 3 times the temperature. And do you know how I get 3 times the temperature? if for every mole of oxygen, I have 4 moles of nitrogen, and you actually take a typical fuel like methane, CH4, and you do the oxygen balance to generate CO2 and H2, you'll find that each mole of oxygen is producing about 2 moles of other gas. And nitrogen is 4 moles, so 2/3 of your, if you got air, 2/3 of your, you've tripled the number of moles that have to be heated up. The nitrogen is there at twice, with 4 moles of oxygen to 1 mole of, 4 moles of nitrogen to 1 mole of oxygen in air. You're going to end up with like 4 moles of nitrogen over here and only 2 moles of combusted gas, okay? And therefore you drop your temperature by about a factor of 3 because you got to heat up 6 moles of gas rather than only 2 moles of gas if you're burning in pure oxygen. And that factor of 3 is what gives you 10 times the velocity, because I told you the combustion intensity goes as T squared, okay? The velocity is proportional to PDV. It's just the heating value of the whole thing. So it's a pretty rough rule of thumb to say it's T squared, but 3 times 3 is 10. And burning a fuel in air is 1/10 as intense as burning it in pure oxygen. I can get 10 times the heat intensity even though I only get 3 times the temperature. Isn't 3 times 3 10? For what I do it is. I mean, you know, physicists use all constants as 1, right? So I'm not a physicist, but nonetheless. Okay, the typical heating value of fuels, you have a plot. Actually, it's better than this plot, but the plot you've got in your stuff is kind of dark for projecting. If I look at the combustion intensity in air for hydrocarbons as a function of the carbon-hydrogen ratio, well, hydrogen is 0, and it turns out methane is going to be right in here, and it should have been on this plot, but I guess it's not. We would fit right in here at, I'm sorry, methane, yeah, methane's over there, CH4. You got propane right here, you've got MAP gas here, and you've got acetylene over here. Well, it turns out the combustion, or the enthalpy value of burning carbon is greater than the enthalpy value of burning hydrogen. People don't realize that. Carbon actually burns hotter than hydrogen. We tend to think of hydrogen as burning hotter because if we think of a hydrogen explosion, or we did something in high school chemistry where we electrolyzed water, we put a little glowing splint in there, and we had the little pop in the glass. Remember that? Okay. It burns very quickly because it's already in a gas phase. Carbon, on the other hand, I burn a log, or I burn a piece of charcoal, and it burns slow because it takes a while to vaporize all that carbon. If you started out with carbon gas and ignited it, it would burn hotter than hydrogen. Okay, but in any case, it really doesn't matter what you have in terms of temperature unless you get up here to acetylene to give you some pretty high temperatures, which is one of the reasons that we use acetylene, and we'll talk about that in just a second. But let's talk a little bit about, well, actually before I do MAP and acetylene, let's do MAP and propane. Just happen to have MAP gas. Although, well, let me go ahead and tell you what MAP is. So MAP is actually a registered trademark, and it stands for methylacetylene propadiene. Well, what's acetylene is just a triple bonded carbon with 2 hydrogens to balance it, C2H2. Methylacetylene is, here's your acetylene, but you got a methyl group over here, CH3, if you're an organic chemist, right? So it's just methylacetylene, and it turns out that gives you C3H4. It turns out propadiene is 3 carbons with the 2 double bonds, and propadiene balanced with your hydrogens actually has the same C3H4. So it turns out methylacetylene and propadiene have the same chemical formula, and there probably is some sort of resonance or something. These things can oscillate between these or whatever. But MAP gas is methylacetylene propadiene. That's why they call it MAP gas. It's a registered trademark. they're not the only people who ever does it, but here we go. Turbo torch map, and you can barely see it, but there's a little register on there, okay? So same torch, okay? There's your map gas, and here we need to do this demo. I'll do it over here. Too many things combustible over there. Okay. And which one burns hotter? Well, I already told you map should burn hotter. This is just a welding wire. You start to see the map over here on the left. Not only is, see it's glowing red, the metal is glowing red, and a lot redder than the propane. So I now know which one burns hotter. I'll wait until this cools down a little bit before I put it down on the. Anybody want to hold it? Okay. Now, the reason I left them burning is they look pretty much the same to you. This one sounds softer. This is harsher on the left, right? The map is burning with a higher velocity because it has a higher temperature, right? More PDV. And so this burning, I mean, it's the difference in temperature is not that great. If I went back to these guys, the flame temperature, this is in air, but it doesn't really matter. This plot is for oxygen. But the difference in pure oxygen between MAP and methacetylene, 130 degrees centigrade. In air, it's probably a little bit less. It's probably 50 degrees centigrade difference, which is not a tremendous difference. But in fact, the PDV, you're getting kind of the square of that difference. And you actually can see it, and you can hear it. Okay? So all things being equal, and in fact, it's one of my favorite demonstrations because I get to burn things in class. And again, you know, I think if the safety office knew I did this, I'd probably be banned for life or something. But anyway, huh? Safety is overrated until you have an accident. So, in terms of the fuel-air ratio, the stoichiometry, this comes. You've got these things, so don't worry too much about them. But this comes out of the welding handbook. And, whoop, that's a little too dark. And so this is the fuel in the mixture by volume. This is fuel gas oxygen mixtures. And this is the normal combustion velocity. And there's going to be a peak in here. This is for acetylene. This is for natural gas, CH4. This is for propane, C3H8. This is hydrogen way up here. On the next page they got over here is the primary combustion intensity, BTUs per square foot. So this is your watts per square centimeter, and you find again your peak heat intensity is when you get your something close to stoichiometric ratio. This X is stoichiometric ratio, and 0 is the neutral mixture, which we don't have to go into right now. And this is secondary combustion. Well, we don't have to go through secondary combustion. Secondary combustion is, you actually, well, we can do it. It's easy enough. You have a primary combustion in the inside cone, and then you have a secondary combustion out here. And basically what happens, you get high enough temperatures that the initial combustion will generate carbon monoxide, and the secondary combustion is where the carbon monoxide gets a diffuse flame out further and burns once again to carbon dioxide. So you get a primary combustion in the center, right here in the cone. Sometimes, like in acetylene, you can actually see a little inside cone, sharply different color, and then you'll see the outside secondary flame. Most of what you see there is a secondary flame. The actual primary flame, there is a little cone in there, and then it starts to spread out and forms the kind of pointed thing. The pointed thing is the secondary flame. The primary flame only goes out to about that distance. Don't hold your finger there too long. Well, I didn't burn it. I just started getting warm. Okay. Anyway, it goes out, in this case, about a centimeter. Okay, for the primary flame. The primary flame cone tip is about a centimeter. The real flame cone tip goes way out here. Okay, for the secondary combustion. Okay. I have burned myself before. Anyway. Okay. What else do we want to say about flames? Let's talk about this. The difference between MAP, we'll finish up with this, between MAP and acetylene. There is a debate among people who market this stuff about whether acetylene is better than MAP for welding. If the combustion intensity is proportional to T squared and the useful heat is the temperature of the flame minus the T of the melt, I mean, that's, if I'm going to try to weld steel, I'm only interested in the melting, in the temperature I've got above the melting temperature of steel. It doesn't do me any good to melt, I mean, I need to get it up hot, but I'm not doing any melting except with the temperature of the flame that's above the melting point of steel. The temperature of the flame up to the melting temperature of steel is just preheating it up to the fusion point. It's the only sensible heat that I have available to input the heat of fusion is the heat of the flame above the melting temperature of the steel. And so the useful heat, or sensible heat, sometimes they call it, is the flame temperature minus the temperature of the melt. And it turns out acetylene has an adiabatic flame temperature in oxygen 3100 C, C3H4, and the marketing people say, well, it's only 230 degrees less. However, if I take that flame minus the melting temperature of steel of 1500 degrees C and square it, I get 256 versus 188 times 10 to the fourth. And so for melting steel, acetylene has a 36% advantage. If you take 266 over 188, you get 1.36. But for flame cutting, which we'll talk about, MAP has distinct safety advantages. What are the safety advantages of MAP versus acetylene? Well, acetylene has this little problem that if you put it under too much pressure, like 150 psi, it tends to explode, which is not a good thing. And acetylene is also difficult to store. I'll bring tomorrow a little canister of acetylene, or a cross-section of a acetylene canister. And the acetylene canister is interesting. If you've ever tried to move an acetylene canister, they're pretty heavy. Anybody know why they're heavy? Because they're not full of gas. They're full of acetone. It turns out because you can't store acetylene as a compressed gas, you have to dissolve it in a liquid. In this case, acetone, having a similar structure, tends to dissolve acetylene, and you can store the acetylene at about 40 psi in the acetone and store much more dissolved in acetone than if you pressurized it as a gas to 40 psi. If you pressurize it as a gas to 40 psi, you only got threefold compression over atmospheric. That's not, you're not storing much there. You can store, I don't know if it's 20 or 30 times that volume if it's dissolved in acetone. The problem with the acetone is you don't want, if one of these things fell over, you don't want liquid acetone coming out. And then you have a big fireball with all that acetone because acetone vaporizes very readily. So they actually have to, and I'll bring it to, tomorrow, they have to put a porous container of a calcium, I think it's calcium carbonate, but anyway, maybe calcium sulfate. But basically they essentially make this porous solid, ceramic solid that keeps the acetone from sloshing around. And if you ever had the tank fall over and the head come off, it would keep the acetone from all just flowing out like, immediately like a liquid. It's sort of like it's absorbed into a sponge, okay? But the whole thing is heavy, and so in fact, if you're doing a lot of use of acetylene, it's still a problem to transport it. And so what they do is you can generate it on site. And it's sort of interesting that what they generate the acetylene from calcium carbide, which is just looks like a regular old powder. But the interesting thing about a calcium carbide is if you drip water on it, and a reactor is nothing more than something that kind of feeds into calcium carbide sand or granules, and just drips a little bit of water on top of this pile of stuff, it forms calcium carbonate, no, calcium oxide, plus, where's the carbonate? Oh, plus acetylene, no. C2H2. Okay? And I think that's balanced. Isn't it? Yep. And so you generate acetylene gas. Now, it turns out the way this was discovered, there's, and I how to bring this in and read it to you tomorrow. There was a guy in North Carolina who was trying to synthesize new chemicals, and this was just after Edison and Westinghouse had started generating electricity. And he developed little arc furnaces, and he was throwing different things into the arc furnace and heating them up in the plasma arc, seeing if he could synthesize some new chemicals that would be useful. And he put some limestone, calcium carbonate, in there with some carbon, and he ended up generating this black sand, which actually happened to be calcium carbonate. And he looked at it and he couldn't figure out what to do with it. So he went and he threw it out into the I think it was the Neuse River in North Carolina, if any of you know North Carolina. And he, for whatever happened as he was throwing this stuff, disposing of this stuff in the water, this was before the Environmental Protection Agency, something caused it to ignite. And he saw this flame coming up off the water as he threw the calcium carbonate on the water. And he decided that's unusual. And so he ended up, that became the beginning of the Press Light Corporation. But anyway, I'll read that stuff to you tomorrow. The other thing that I like the story is at Newport News Shipbuilding once, they told me the story of the guy, welding engineer, sitting in his office, and he hears the fire alarm going off, and another engineer comes in and says, oh, there's a fire down at the carbide shack, because there they generate their own acetylene and pipe it around the shipyard, and they have the calcium carbide and they drip the water on it. And the guy says, he says, there's a fire down at the carbide shack, but it's okay, the fire department's on the way. Well, the senior welding engineer shot out of there to get there before the fire department got there and spread water on the thing. Because it could be really exciting if you had a carbide shack fire and you start spraying water on it. It could be real exciting. Okay, as you generate more fuel with the water. Okay, so see you tomorrow.